Okay, real talk. What is math and why is it awesome?
Some people think that math is just numbers, equation, and some boring stuff like that.
Boring!
But it's so much more than that. Math is the language of the universe.
Have you guys noticed how flowers grow in spirals? Or how sunflower seeds follow a perfect pattern? That's math in nature. Fibonacci sequence is everywhere.
First up, fold symmetry. Ever seen a paper folded in a half and it looks like the same on both sides? That's what we call fold symmetry or reflection symmetry. It's like a flipping a mirror image of yourself.
Fold symmetry is all about balance. It's nature's way of making sure things are equal and perfectly aligned.
Now let's talk about patterns. Patterns are everywhere, and math helps us see them.
Logic pattern is the ability to discover meaningful patterns in strange and unpredictable situations. So here's an example of logic patterns. Example number 1, shape pattern. The problem is, what comes next in cone, spear, cone, spear? So here's the solution. Identify the pattern. The shapes alternate between a cone and a spear. Next, predict the next step. After the spear, the next shape is a cone, so the answer is a cone.
Geometric pattern is a motif or design that depicts abstract shapes like lines, polygons, and circles. For example, imagine a pattern of hexagons tiled next to each other like a honeycomb. Each hexagon has 6 sides, and because of their shape, they fit perfectly together without leaving any gaps, forming a continuous, repeating pattern. The repetition of these hexagons creates a visually pleasing geometric design.
Number patterns are a group of numbers that follow rules. They can use input or output tables to create sequences. There are 2 types of sequences, arithmetic and geometric sequence. For example, in the sequence here, to get from one term to the next, you always add 4. In the sequence, to get from one term to the next, you always subtract 2. If a sequence has a rule where to get the next term, you always add or subtract the same number, we call that arithmetic sequence. Next is geometric sequence. Let's take a look at this sequence. In this one, to get from 2 to 4, you would add 2. To get from 4 to 8, you would add 4. And 8 to 16, you would add 8. Since the difference is not the same, we know that this is not an arithmetic sequence, but a geometric sequence.
Word pattern. Word patterns can be observed in language through morphological rules, such as how nouns are pluralized or how verbs are conjugated for different tenses, as well as through metric rules. For example, book, library, star, galaxy. Did you notice the pattern? These examples illustrate how individual items relate to larger group or categories. Here's another example. Cat, cats, child, children. Here, the pattern is pluralizing nouns. The singular noun cat is made plural by adding s. The singular noun child changes to children, which is an irregular plural form. Each of these examples contributes to our understanding of both mathematical concept and natural language. The emphasis here is on patterns in structure and syntax, which are essential for the broader study of language and digital communication.
Now, let's talk about one of the coolest patterns in nature, the Fibonacci sequence. It's simple. You start with 0, then 1, and each number after that is the sum of the 2 before it, like this: 0, 1, 1, 2, 3, 5, 8, 13, and so on.
The crazy part?
Act like an angel and dress like crazy.
This sequence is everywhere in nature. From the number of petals on a flower, to the spiral shapes in shells, and even galaxies in space.
Speaking of spirals, have you ever heard of the golden ratio? It's a special number about 1.618. When you use this ratio, you get the most perfect proportions. It's like nature's secret formula for beauty.
So which is mathematics? A discovered part of the universe or a very human invention?
It's actually a mix of both.
It's an intricate combination of inventions and discoveries.
Examples like 1, 2, 3, 4, and 5, and many more.
He invented the concepts, but then discovered relations among the different concepts.
That's why it makes a great math history.